In order to find a more accurate, defined shape of our graph, we need to find the second derivative of our function. And since it's crazy hard, look at that. I'm Mr. Budzyn. I'm telling you, plug it into your calculator because there's no way, like, plug it into your calculator and get an answer. Alright. And the second derivative is, alright, from this, we set our second derivative equal to 0 or undefined. Alright, in order for the second derivative to be equal to 0, you have to set the numerator equal to 0. So it is going to be -2 equals 0. And since that can never happen, like, no, that's a big no, so it can never, ever happen. And to set it undefined, you have to set the denominator equal to 0. Split that bad boy in half, and we're going to get, throw that over, it's irrelevant, so it's going to be 0 equals x minus 2. Add 2, 2 equals x. And same thing, you throw it over, x plus 1 equals 0, x equals -1. These are critical numbers. With these, you plug them back into the original function to find critical points. They're going to be
-1, 0. Mr. Budzyn, haven't we already found these?
Yeah, we already found them.
And it's going to be 2, 0.
But we're going to find them again. Alright, and then these, we're going to, right here, these are PPOIs. P-P-O-I. P-P-O-I. Alright, now we're going to do the second derivative test. And our intervals are going to be
Negative infinity to -1. And -1 to 2.
1 to 2? To 2.
And 2 to infinity.
Infinity. Alright, and now when you plug a number like -10 into the original, you're going to get?
A positive.
A positive. Concave. Oh. When you plug 0,
A positive.
and then when you plug in 10 to the second derivative,
Negative.
you're going to get negative. Conc up, concave down. Oh! Oh, look at this! There's another change! There is a change in concavity, which is a P-O-I. It's a point of inflection, point at which concavity changes. So we're going to come over here, and since we have a better understanding and knowledge of what this function is going to look like, we're going to go ahead and graph it. I'm going to start from down, and we know it increases all the way up to a sharp freaking point. That thing cuts you. And then we're going to come back down to here, and it levels out here. And then it's going to come back up and shoot that way. You see that? So we know that this is still a possible point of inflection, and this is not a possible point of inflection anymore. It is a point of inflection because we proved it right here in the second derivative test. So now, let's explain this graph. For all this hard work, we know that this graph looks something in this form. Actually, pretty exactly. This is pretty exact to the real one. We know that it starts, you see? Look at this Hello Kitty bad boy. I'm not scared of my manlyhood. It starts from increasing, and then all of a sudden, at that peak right there, it just goes BAM! And it changes over to negative slope. And this is concave up now. So it goes there, down, down, and evens out right here. Right here, the tangent line is 0. Slope equals 0 right here. And then it comes up again right here, increasing. And then right here, it goes from concave up to concave down, right here. And this point, right here, 2, 0. That's a point of inflection. Bam! And then it goes all the way up, increasing. And that is, we forgot the range. The range of this function, range, we can now see that is from negative infinity to positive infinity. It goes the whole range. So it's going to be from negative infinity to positive infinity with parentheses, not brackets, because you can never calculate infinity. Jessica is going to show us what it looks like on the calculator, so I can show how much of a freaking beast I am at drawing functions on the board, freehand. Show it to us. Green graph, we already have it in. You go to y equals and then you graph it. Beam! Look at that. Look at that beauty. Oh, and as you can tell, there's no asymptotes here. There are no asymptotes.
Is this the real life? Is this just fantasy? Caught in a landslide, no escape from reality.